As you can see, this discussion is about exponential functions. And simply stated, an exponential function is any function for which a variable is used in an exponent, part of a variable expression that's an exponent. Now, the most basic type of exponential functions are functions of this form. And that would be where we simply have some constant to a power that is a variable. That's the most simple type. So examples would be f of x is equal to 2 to the x power, or g of x is equal to, let's say 1/2 to the power x, or even h of x is equal to pi. Now remember, pi is a fixed number. It's not a variable, to the x power. So the idea is we have some constant to a power of x. This is the most basic type. Now, I might say that the only time that we consider this is if a is not negative or 0. So a has to be between 0 and 1, and if a is 1, it's not interesting, or bigger than 1. So we don't use negative a's, we don't use a as a 0, we don't use a 1. 1 to the x power is always 1, 0 to the x power is always 0. Well, in fact, they wouldn't even define. 0 to the negative 1 power would be 1 over 0, wouldn't it? So sometimes that's not defined. Anyway, that's the idea. Now, in some cases, we can answer some questions we can evaluate pretty simply. So we might be asked to evaluate the following. Or f of x is equal to 2 to the x power. So for instance, we might be asked to find out what f of 1 is. Well, f of 1 would be 2, see our x is 1, so it would be 2 to the first power, which is just 2. And we might be asked for f of negative 2. So we've got to know about rules of exponents here. Well, that means our x is negative 2, and our x is our exponent, so that would be 2 to the power negative 2. And of course, remembering how we deal with negative exponents, that would be 1 over 2 to the power positive 2, which is 1/4. If we were asked to find f of 0, then our x is 0, so that means our exponent is 0, and 2 to the 0 power, if we recall, is simply 1. Now, sometimes we could be asked to find out what f of 1.5 is, okay? And that means our x is 1.5, so we would have an exponent of 1.5. Now, we can't do this any further without using a calculator. And when we use a calculator, we'd have to approximate. In just a moment, I'll get out my calculator. But before we do that, I would like to point out to you that we can give some kind of rough estimate, that we know 2 to the 1.5 certainly is going to be smaller than 2 to the second power, since 1.5 power is smaller than the power 2, and it's got to be bigger than 2 to the 1 power. And so if we look at this, that we know whatever result we get is going to have to be between 2 and 4. 2 to the 1.5 power is some number between 2 and 4, and it will, of course, have decimals on it. So we'd have to work that out, and we'll do that. In fact, we'll pause here to do that with our calculator.
Well, as you see, I've got my calculator out, which is a TI-83 Plus, and we're asked to find the value of 2 to the power 1.5. Well, the way we do this on a graphing calculator, particularly a TI graphing calculator, is that we want to put the value 2 in, so we'll enter 2, And then we want to enter an exponent, and the exponent happens to be 1.5. Well, the key that you see right here looks like a little housetop. It's called a caret. That's the exponentiation key. So when we press this button, then what we enter right after that will be the exponent that we're putting on 2. And so we'll enter the exponent 1.5, and then we're ready to get that value, which is we press enter, and you can see it gives us a long string. Now this is actually an irrational number. Remember, before we said our result would be between 2 and 4, and certainly it is, isn't it? It's 2.8, almost 3. But we would probably be asked to round this answer, and maybe to 4 decimal places, and that's to the right of the decimal. So that means we would round to this position right here. And since the following digit is less than 5, then we would just truncate. We would round to 2.8284. And I'll enter that on our page as we continue going here.
Well, you see I've entered the approximation, and in the process I've rounded it to 4 decimal places to the right of the decimal point. Now, in the next couple of these, well, let's look at another example. Okay, so here we're given an exponential function that's a little more complicated. And in this case, the function is g of x is equal to 5 to a power that is x plus 3. 5 to a power that is x plus 3. And then, not part of the power, we have a plus 2. So here our exponent is more than just the variable x. It's a little more complicated, but certainly we have an exponent that involves a variable, and that's what makes it an exponential function. So in this case, we're asked to evaluate g of negative 1, which just simply means we need to replace each x with a negative 1. So this would look like 5 to a power, rather than x plus 3, negative 1 plus 3, and then the plus 2. And so we just do a little bit of work here, of course. We add negative 1 and 3 in our exponent to get a 2, so our exponent is actually 2. And so we have 5 squared, of course, which is 25, plus a 2, and in this case, g of negative 1 then is 27. Now on the next page, we'll work on something that we have to use our calculator on to be able to be successful, and so we'll pause temporarily. I guess to you it doesn't seem like we're pausing. Well, what we see here is a problem where to evaluate h of 3 when the function h is given by h of x is equal to e to a power negative 0.5x. Now, there's 2 or 3 things about this that we have to be concerned with. And the first thing is this thing e. And the way I normally do this in class is I first talk about pi. And we all have some feeling for the number pi, and it has something to do with circles, and most of us don't really remember the relationship pi has with circles. And we could go into that now, but that's not really the discussion that we need to have. And usually when I ask, well, what is pi, meaning what's the significance of pi and what is it for, someone says, oh, well, pi is 3.14. Well, that's not actually accurate. You notice I put that little squiggly equal sign. Pi is approximately 3.14, but we could continue this decimal as 3.14, 159, 2654, and it goes on and on and on forever. Pi is an irrational number, which means it can't be written as a fraction, and as a decimal, it never stops going, and there's never a completely continuing repetition to the way the decimal is written. So, and that's about all we really get out of it, that pi is something to do with circles, and it's an irrational number that's approximately 3.14. And the reason we use the letter pi is exactly the Greek letter pi to symbolize it is because we never can write it down exactly. So pi represents the exact value of that number. Well, e is something similar. E represents an irrational number. Now, that irrational number is kind of like with the pi. It's not that we need to know so much about the significance right now of the irrational number. E is really a number that's approximately 2.71828 and so on, okay, ... Now, the first few digits may look like we see a pattern, but if we continue this decimal forever, and that's why we call it E, then there's not a pattern that completely repeats throughout and throughout and throughout forever and ever in this decimal. The decimal goes on forever. Now, E occurs very naturally, and it particularly occurs in nature where we have things that are increasing at a type of rate, an exponential rate, or decreasing, like radioactive decay, or population growth, or certain kinds of interest on money have to do with the number E. So let us remember now, when we're looking at this is similar to what we had before when we said f of x, when we talk about f of x is equal to 2 to the x power. In this case, the constant is the number E, which is about 2.72, okay? But we'll just leave it as E because we'll have to use our calculator to calculate this. Now, I don't know that I'm going to actually get my calculator out, but here's what I want you to realize. When we're using our calculator to calculate this value, see, here's what we're asked to do. H of 3 is equal to e to a power that's negative 0.5 times our x value, which is 3. Now, we might be able to do some of this in our head. We might be able to do the 3 times 0.15 in our head and say, oh, this is e to a power that's negative 1.5 when we multiply those two together. And that would be all right, and then we could use our calculator, and the way we would use our calculator is that we would enter an E, which is, on a graphing calculator, you have to press second and then the division bar. So we would enter an E, and remember, that's the second key, it's called the second, and the division bar keys, and that will give us the E. And then we press the caret key, the caret that looks like a little house top, and that's an exponentiation key. And then we would press the negative key, okay, to get this, okay, we actually press a key that's at the bottom that is in parentheses. That's a negative key, not a subtraction key. And then we would enter the 1.5. And if we did that, it would fill up our screen with a decimal. Let me see if I can do that right now. So our E key to a power of negative 1.5. And it would give me approximately 0.2231 if I round it to 4 decimal places. Now, there are other things that we sometimes need to be concerned about because we could have done this more directly. We could have just left the multiplication. That is, we could have said, let's just deal with this and not try to do any of the arithmetic in our heads. Well, if we do, we need to be careful. The correct way to enter this into our calculator is to get the key, the E value, which is the second and division together, and then put our exponentiation key in, and then we would need to enter parentheses, and then use our negative key, not our subtraction key, 0.5 or just 0.5, and then our multiplication key, and then 3 in close parentheses. Many times, and if we did that, we would get the correct answer, okay? And we'd find out that that's approximately 0.2231 again. Of course, that should be the same value. What would be wrong, and I'm making a big X by that now, a lot of times I'll have students that will get the E correctly, and then they'll put the exponentiation key, and then a negative 0.5, or just negative 0.5, and then a times 3. Of course, see, the difference is that we don't have any parentheses. Now, the way your calculator, and so this is wrong, the way your calculator interprets that is e to the power negative 0.5, and then after it calculates that, multiply with a 3. In other words, that 3 doesn't have anything to do with the exponent. And that would give us an incorrect answer. In fact, I'll tell you what that answer is after I calculate here. In this case, I get a negative, if I do it this way, I get a negative 4.0774. And you can see there's a big difference between those two answers. Well, this is wrong because we forgot the parentheses to tell the computer or the calculator that times 3 was part of the exponent. Those parentheses are necessary. So this would have been the correct way to enter that.
As you can see, I've had a change of heart that I want to actually demonstrate this using the calculator. So recall, and I'm going to do first so that we can see. It's hard to see on this calculator, but if you have a TI-83 or a TI-84, the E is right here, and I know it's hard to see, and it's in gold. And the gold things above the keys mean that we have to press this gold key here, which is second. So to get that E, I press second. Oh, I've got to turn my calculator on. Let me clear what we've done before. I press second, and then this division bar, and you can see E will show up. And just to give you that idea again, if we press enter here, it will actually give us the value E. And I mentioned earlier, I didn't put these down, but it almost looks like there's a pattern. But if we let this decimal actually continue, this pattern stops, and it's not a repeating pattern forever. Okay, well, let's clear this. We're asked to find e to the power negative 0.5 times 3. So the correct way to do this is to press second and the division bar, key, so that we get our e, and then we press our exponentiation key. Now, to do this correctly, without doing the calculation in our head, as I said before, we could just enter the exponent negative 1.5, because negative 0.5 times 3 is negative 1.5. So we could do that. Now, to do that, we use this key right down here for the negative. This key is a subtraction sign. Okay, so this is the negative, and then we'd put 1.5, and whatever follows that house top is the exponent that we're using on e. And when we press enter, then, as I said, we get 0.2231, which is exactly what I wrote down earlier. Okay. Now, if we wanted to do this directly without doing that multiplication in our head, then we would do as I mentioned before. We'd get our e, so that's second division. Okay, and the problem with, okay, let me do it wrong first. The problem with, we put our exponent and then putting a negative 0.5 as our exponent and then times 3. The problem is it's what follows the exponentiation key that is used as the exponent. And so right now it thinks the exponent is only negative 0.5, and after it calculates e to the negative 0.5, it will multiply that result with 3. And so if this is what we do, oh, I guess I wrote down something incorrectly early on. When I wrote down this approximation, I guess I did not get, okay, I did not get negative 4.074, and that's just my error. But you see that I didn't get what I was supposed to get above, because I knew the exponent was negative 1.5. The correct way to do this, second division gives me my e, then we put our exponentiation key, and we want to show the calculator what our exponent's going to be, and our exponent's actually a calculation. So we put parentheses, and what goes inside the parentheses is our calculation for the exponent. So it's a negative 0.5 times a 3, and then we close our parentheses. So that calculation that's between the parentheses ends up being the exponent that we're using. When we press enter here, you notice that's exactly what we had above. So apparently my earlier calculation was wrong. I don't know what I did. But anyway, that just shows you the use of the calculator one more time. Okay, let's move on then in our discussion.
Ideas of the graphs of these exponential functions, these basic exponential functions, and really the issues that I'm concerned about is what does the graph look like generally, and what are the three important pieces, the domain, the range, and any asymptotes, in this case horizontal asymptotes. So we'll do that on the next page. Next, we want to turn our attention, as I said, to graphs of these basic exponential functions. So in the basic ones, for instance, I'm sorry, and they actually fall into two categories, and it depends on what the base is. Remember, this value, this constant, is called the base, and of course the variable, the x, is the exponent, as we understand. So, like I said, they fall into two categories. In the case that the base is greater than 1, remember, before we get too far into this, remember we made sure that our a value had to be greater than 0, but not equal to 1. And so that means we have a values that could be between 0 and 1. And we could have a values that are actually bigger than 1. So the two categories we have depend on these values. That is, if a is bigger than 1 is one category of these exponential functions. And so examples of that would be like y is equal to 2 to the x power, or y is equal to 4 to the x power, or y is equal to 1.1 to the x power, or even y is equal to e to the x power, since e is 2 point something. Now, in all of these cases, we'll be a little more precise here in a moment, but in all of these cases, these graphs have a similar look. They're not the same, but they have a similar look. They'll all look something like this. Okay? Every single one of them. Of course, this is the x-axis, and this is the y-axis. And so in all of these cases, we could say something about the domain. The domain here is the set of all x's such that x is greater, the set of all x's. So it's all real numbers, and I really goofed that up. So the domain is all real numbers. Now in interval notation, remember the way we write that, from negative infinity to positive infinity. Now the range, on the other hand, those are the y values, and just because of what I've told you, we can look at that graph, and we understand that the way I've drawn the graph, that the graph is never going below the x-axis, and so we have y's that are always positive. So the range is the set of all y's such that y is greater than 0, never equal to 0, and negative, never negative. And there is also a horizontal asymptote. The way I've drawn the graph, you could suspect that. Now in this horizontal asymptote, it just gets close to the horizontal asymptote on one side of the graph, in this case the left side of the graph. And that horizontal asymptote is the line y equals 0, which of course is the same as the x-axis. Now, if our a value is a positive number between 0 and 1, so that would look like things like y is equal to 1/3 to the power x. Our a is 1/3, or y is equal to 0.75 to the power x. Well, those graphs have a similar look, but if you will, they're kind of in reverse order. That is, these graphs will all look something like this. So once again, the domain is the set of all real numbers. You see, we're using all x's here. We go, and that makes sense. We can use any value as an exponent, and x is the exponent, isn't it? We can use any value. So the domain is the set of all real numbers. That is from negative infinity to positive infinity. Once again, the range, those are the y values. Well, the range are y values that are strictly greater than 0. Never equal to 0 and never negative. And we'll talk about that here in just a moment. And also, this has a horizontal asymptote that is the line y equals 0, which is the x-axis. Now, this time it's getting close on the right side as opposed to the left side. Well, let's see why the graphs look the way they do. And we'll just sketch the graph of f of x is equal to 2 to the x power. Now, to do that, we're going to actually create a table of values. Okay. So, for instance, we could choose x to be 0. And if we did, then y would be 2 to the 0 power. And 2 to the 0 power we know is 1. Okay, so 0, 1 is on the graph. We could choose x to be 1. And if we did, then y would be 2 to the first power, which is just 2. And we could choose x to be 2. And then y would be 2 to the second power, which of course is 4. And then we could choose x to be 3, and then y would be 2 to the third, or 8. And you can see that the y's are getting big. I mean, even, we probably wouldn't do this, but we could choose x to be 10. And then we'd have 2 to the 10th power. And 2 to the 10th power is 1,024. So it gets big very quickly. Okay. Well, now, what I haven't done, let me set up our graphing, our coordinate axis over here, and we'll plot these points. Okay, let's get started then. We'll plot 0, 1. Well, 0, 1 is this point. Now, let me make a point of this. Notice also, if y is a to the x power, whether a is bigger than 1 or between 0 and 1, if x is 0, then y is a to the 0, which is 1. So the point where x is 0 and y is 1 is on every one of these graphs, isn't it? Okay. Now when x is 1, y is 2, so that's this point. And when x is 2, y is 4, so that's this point. And when x is 3, y is 8, and that's this point. And of course, if I went out here to 10, maybe about here, it'd be, y would be 1,024, so it's very, very high very quickly. Now, what I haven't done is chosen any negative x's, so I could choose -1 for x. Then y would be 2 to the power -1, which is the same as 1/2. Well, then if x is -1, here's -1, then y is only 1/2. That's about right there. If I choose x to be -2, you'll see real quickly that y is 2 to the power -2, which is 1 over 2 squared, which is 1/4. So y is 1/4 when x is -2. Well, that's right here. Okay. You see we're getting close to that x-axis. If x is -3, then y is 1/8. Well, here's where -3 is. 1/8 is even closer to that x-axis, isn't it? But now here's the next thing to think. 2 to any power, okay? 2 to any power, no matter what that power is, it's going to be something that is greater than 0. So 2 to a power can't be 0. 2 to a positive power is just a big positive number. 2 to the 0 power is just a 1. 2 to a negative power is just a positive fraction. So 2 to any power will always be positive and never 0. So as we graph this, then you can see what I was saying before, the way this graph looks. Oops. And the bigger our negative exponent is, so for instance, we chose x to be -2, then our y value would actually be 1 over 1,024, still positive, but just barely above that x-axis, isn't it? And so that's the idea of what these graphs look like. Now, we could do the same thing with the graphs that we looked up here. It'd just be a little more challenge calculating the points to plot. But I assure you that's the way they'll look generally. Okay, well, let's use the information that we know what these graphs look like generally, the basic graphs. And also how we know something about the transformation techniques in graphing. And let's graph something that's a little more complicated than the most basic of these functions, these graphs. So we're asked to graph h of x is equal to 3 to the power x subtract 1, the power is x minus 1, and plus 2, which is not part of the power. Now, as we consider this, let me rewrite it down here so I can kind of scratch it up a little bit. As we consider this, there's 2 things that make this graph different than the original ones that we talk about, and it's those 2 pieces right there. See, without those 2 pieces, it would just be y is equal to 3 to the x. And we have a basic idea of what that looks like. So we need to know what that minus 1 and that plus 2 caused to happen. Well, if we're subtracting or adding a number from the exponent in the numerator, where the exponent is a variable, that minus 1, that is a horizontal transformation. Okay? And since it's horizontal and we're subtracting, that's actually going to be right, isn't it? Instead of left, it's going to be right 1 unit. Now this plus 2 is after we do all the calculations with the exponent. Say that's we get a y value partially, and then we add 2 at the end to finish out that y value. So this is a vertical transformation. Causes a vertical transformation. And vertical transformations move in the direction we expect them to, don't we? So this is going to go, because it's plus, it's going to go up 2 units. Now we're talking about transforming this basic function, aren't we? So we set up what that graph would look like, roughly. Let me set that up. Okay, so what I've sketched in here is y is equal to 3 to the x power. And remember, we know that this will go through the point 0, 1, and I just sketched another one. If x is 1, then y would be 3, and so that's this point right here. Now, what are we going to do? We're going to move this graph right 1 unit and up 2. So let's just follow a couple of the points. This point right here is going to go right 1 unit, that's over here, and then up 2 units, and so it's going to end up being there, isn't it? This point's going to go right 1 unit, and then up 2, and so it's going to be right there. So our 2 new points that we're following when we move right 1 unit and up 2 will give us a graph that looks, remember, it's going to go through this point, and it's going to go through this point, not the one down below. But now here's the problem, is what's happened. Remember, this graph doesn't keep going down, down, down. In fact, our new graph has been raised up 2 units. So the horizontal line it's going to get close to is no longer the x-axis because it's being raised up 2 units. So it's going to get closer and closer to this horizontal line that goes through 2 since it went up 2 units. And so as we sketch our graph then, it's going to look more like this. That's the graph shifted right 1 unit and up 2 units. Now, we have a few more things to worry about here. What's the domain in this case? Well, the domain is still a set of all real numbers. What's the range in this case? Well, we've moved the graph up, haven't we? So the range is the set of all y's, but this time the y's are greater than 2 instead of greater than 0. They'll always be bigger than 2, never equal to 2. And that's why we see this horizontal asymptote that I've dashed in there. In fact, the horizontal asymptote is in fact that line y equal 2 now, the horizontal line y equal 2. And so we've got the graph done to the, appropriately. Now, if we were asked to sketch, for instance, g of x is equal to the negative of 3 to the x, the only transformation we have here is that negative sign. And that causes a reflection. Now, because it's not on the x, it's after the x has been used into the exponent, that's a reflection about the x-axis, not the y-axis. So if we thought about the original graph of y equals 3 to the x, which would look like this, if we reflect that in the x-axis, then we're going to actually have a graph that looks like this. So this will be y is equal to the opposite of 3 to the x. Now, once again, here the domain is still the set of all real numbers. But the range is different because this actually has negative y values. In fact, the range is a set of all y's such that y is actually less than 0. All of our y's are negative. But it so happens that the horizontal asymptote is still the x-axis here. The y equals 0, which is the x-axis. Well, on the next page, we're going to kind of change gears a bit and talk about solving exponential equations. That's equations that have variables and exponents. Sorry for the delay there. As you see here, and I mentioned, we're going to solve some introductory exponential equations. So we're looking, in this case, for the value of x that makes this equation true. And we might be able to do this by simply what I call the old eyeball method, try a few values of x and see which one works. And we might even decide that x has to be 3, because if x is 3, the exponent is 4, and 2 to the 4th is 16. But our problems, of course, get more difficult than this, and so we want to kind of have an idea or a technique for solving equations of this type. This won't work for all types of exponential equations, but for the ones in this section that we're discussing, it will. So here is the idea behind it. We try to get each side of the equation to have the same base, that is, the same number to a power. And so what we notice with 16 can be written as 2 to a power. It's 2 to the 4th power. And once we do that, we have 2 to a power on one side is identical to 2 to a power on the other side. And so it must be true that the powers themselves have to be equal if the two sides are equal. And then we have an equation we can easily solve by just subtracting, of course, 1 from each side. And we would get x equals 3. So the solution here, as we did with eyeball, we come up with x equals 3, and we could easily check it. And if we were checking it, that's exactly what we would do. We would replace on the right side our x with a 3, and then we would just see whether the two sides are equal. And of course, on the left side, we have 2 to the 4th, and since we know 2 to the 4th is equal to 16, then we know that we have found the solution. Okay, well, let's increase the difficulty a bit. Let's solve this equation. And here we have 1/5 to the power 2x is equal to 25. Now, what we're trying to do, once again, is we're trying to write both sides of the equation as some base to a power. And I might point out that real easily with 25, we recognize that's 5 squared. But of course, on one side of the equation, we have the base 1/5, and on the other side, we have the base 5. 1/5 to a power equal 5 to a power doesn't tell us a whole lot. So the way we would approach this is we would see if we could write this 1/5 as 5 to the power. And we'll recognize, notice, that 1/5 is really 5 to the power -1, isn't it? So rather than writing a 1/5, we could write it as 5 to the -1, and then that 1/5 has an exponent of 2x on it. Now, on the left side, we can use laws of exponents and replace that x5 to a power raised to a power. What do? We multiply the two powers together. So we have 5 to a power that's -1 times 2x on the left, and 5 to the 2 on the right. And of course, -1 times 2x is -2x. So we've been successful in writing both sides of the equation as 5 to a power. And so if that's the case, then the two powers themselves need to be equal. And then we have a simple equation to solve from there by dividing on both sides by -2. And so we get x is equal to a -1. And we can easily check that as well. Well, the next example is even a little more involved. In this case, we're asked to solve 9 to the power -x plus 1 is equal to 27 to the power x. The issue here is we can't write the left side as 27 to a power easily, and we can't write the right side as 9 to a power very easily. But we might recognize that in each side, the 9 can be written as 3 to a power. That's 3 squared is 9, isn't it? And so the exponent that's on that 9 is a -x plus 1. And likewise, 27 can actually be written as 3 to the third power. And so that 27 has an exponent on x of it. And now we see that we can use rules of exponents, and we'll have 3 to a power is equal to 3 to a power. Well, on the left side, we multiply the power 2 with the power -x plus 1. And on the right side, we multiply the power 3 with the power x. And so as we simplify that, let's come up here. On the left side, 2 times the power -x plus 1, we end up with -2x plus 2 as our power. And on the right side, 3 times x, we end up with our power as 3x. So we have 3 to a power is equal to 3 to a power. So the power -2x plus 2 must be identical to the power 3x. And now we would simply solve this equation for x. And to do that, we would need to add 2x to both sides. And then we need to divide out the 5. And so we end up with what? X is equal to 2/5. And we never would have been able to eyeball that. Now, checking this would be a little more difficult, of course, but we certainly could check it. It's just that it would be difficult for us to do. Okay, let's get one that's just a little bit different yet. What if we had an equation that looked like, let's say, 3 to the power x squared is equal to 9 to the power x. You've kind of seen the system that we've gone through, and so what we could do in this case is we could write the right side and replace the 9 with a 3 squared, and so we have a base of 3 introduced on both sides. So we have 3 to the power x squared is equal to 3 to the power 2x. And so the power x squared must be identical to the power 2x. and now we need to solve that equation for x. And to do that, we would get all of our x terms on one side and then factor. And we see that x is a common factor here that we can factor out, and then we'll set each of those factors to 0. We have two factors, don't we? Each of those factors to 0, and of course one solution is x equals 0, and the other solution would add 2 to both sides as x equal 2. So we actually have two different solutions here, and that's not entirely unusual. On the next page, let's do one more just to give us a sense of what things can look like. Okay, here is something that's a little different. And the issue here is obviously the way it's written. We can't write each side as 2 to the power because we've got that pesty plus 5 there. So we really need to simplify this. We really need to get this 2 to the x alone. And to do that, we need to subtract this 5 on both sides, don't we? And if we do that, we'll have 9 subtract 5 is equal to 2 to the x power. And 9 subtract 5, of course, is 4. And then once we've accomplished that, we don't even need to go through the extra pieces here. We can clearly see that what power we raise on 2 to get a 4 is simply 2. 2 to the 2 power is 4. So our solution in this case is x equal 2. Okay, we're going to end this section with looking at a graph and deciding what the function is, what the function is for the graph that we're looking at. So let me set that up. Okay, here's our problem. Determine the function whose graph is given, and here's what we know. The function is of the form y equals some constant to the x power. And we also know two other things. We know we're given 2 points that are on the graph. The point that I've pointed out here has an x value of -1 and a y value of 1/5. And the other point that we're given is the point that we see right here, and that has an x value of 0 and a y value of 1. Okay, those are the two pieces of information we're given. Now, we're looking for, we know it's of this form. Okay, we know it, oops, I got it. We know it's of this form. And so all we really need to do is find out the a value. And that probably isn't too difficult because we know this point. Remember, this point's on the graph. And that says if x is -1, then y is going to have to be 1/5. So if we replace what we know is true about the equation, that when x is -1, y is 1/5, and so we have an equation that looks like that when we fill in that x and y value. And now the only unknown is the value of a. So we ought to be able to solve this equation because a to the -1, of course, is 1 over a. Now what would we do here? We would probably try to eliminate all the denominators. So we'd multiply on both sides by the lowest common denominator, which would be 5a. We'd multiply both sides by 5a. And of course on the left side, the 5 is going to cancel, leaving a. And on the right side, the a's are going to cancel, leaving 5. And so that tells us that our function, we know the a value now, don't we? Our function is y is equal to a, which is 5, to the x power. That's the graph, that's the function whose graph we are looking at. Now the next one's going to have a little twist in it. We'll do that on the next page. So let me set that up. Okay, you can see in this problem we're to determine the equation of the function that we see graphed. But we're told this time the function is of the form some constant c times some constant a to a power. So in this problem, we need to figure out what c is, and we also need to figure out what a is to be able to have the function. Now, the other thing that we're given here is that we know 2 points on the graph. One of the points is the point 1, 6, and the other point is the point 0, 3. Those are the 2 points we know are on the graph. Now, Let's consider this point first.
Yeah.
Okay, let's consider
Yeah,
this point
yeah.
first. We know that the equation looks like that, and we are given an x value and a y value. If we put that y value and x value into this equation, then it's going to look like this, which we still have two unknowns. But the significant part of this is a to the 0 is nothing more than 1. So this becomes 3 is equal to c times 1, or simply c is equal to 3. So using that point, that in this case, that y-intercept, we've determined the value of c. So now we know our function actually looks like y is equal to 3 times a to a power, and it's the a that we don't know. So we use the other point, and the other point is 1 comma 6. That means if we use this x value and this y value into the equation, we know the equation is true. Well, in this case, the y value is 6, and the x value is 1. And so when we substitute those into the equation, we have something that looks like this. Well, of course, a to the first power is just a. And so in this equation, we ought to be able to solve for a by dividing on both sides by 3. And so we get a is equal to 2. Now, those two pieces together tell us exactly what the equation is, or the function is that we see the graph of. It's y is equal to c, which is 3, times a, which is 2, to the x power. That's the equation that we're looking at. That's the graph that we're looking at. Well, I think I'm going to stop here with our notes for the introduction to exponential functions. And I think this will get you far along in your homework. Good luck on your homework.
Can't just have everybody order. Strange, hold on.